This is Jack Jackson, continuing our series of videos here connecting probability and statistics with calculus. In this video we're going to be talking about the mean, variance, standard deviation, and skewness, and even also the median of a continuous distribution and how to compute those things. Oftentimes when we're looking at a distribution, we're interested in describing that distribution of data, or the distribution, the characteristics of the graph is another way to say the same thing. And so we're interested in various characteristics of that. We might need to know the center, and the center of that distribution is what we call the mean, mu. That's one way to measure it. The median is another way to measure it. We could also measure the spread of our data. That's measured by the variance or the standard deviation. And we might want to measure if it's symmetric or not. And so the deviation from symmetry is called the skewness of the distribution. And all of these things can be computed using calculus when we have continuous distributions. So let's start with the mean. Let's find the mean of a uniform distribution. Now, the mean, we use the Greek letter mu here for the mean. It's also known as the expected value of x. And the way we do that is we integrate over from minus infinity to infinity x times the p of x. P of x is the PDF of x. Now, for a uniform distribution, the function is just 0 to the left of a and to the right of b, so we can ignore that. This integral doesn't give us anything for that. And so this integral is the same thing as just the integral from a to b of x times 1 over b minus a. Well, that's just we can take the 1 over b minus a out front, and we're integrating x, which is just 1/2 x squared is our antiderivative, and then we evaluate from a to b. So we're using the fundamental theorem there. When you plug in b, you get b squared. When you plug in a, you get a squared. The 1/2, the 1 over b minus a, we factor out. So we get 1/2 times 1 over b minus a times b squared minus a squared. We can factor b squared minus a squared as b plus a times b minus a. That difference of squares factors as a sum and difference pattern. And notice that the b minus a's will cancel, and so you're left with a plus b, or b plus a, over 2. Now, intuitively, this ought to make a lot of sense, because think about the graph. The only part that really matters is this little line segment on the PDF that runs from A to B horizontally. Well, what we're doing when we're finding the mean is we're finding an average. It's not an average of the y's. We talked about how to do that in an earlier video, in general, how to find f average. But this is rather an average of the x's in some way, a weighted average of the x's. And so or another way to say this would be an x value of a center of mass, a balance point. It's another way to think of the mean. Well, in the case of a horizontal bar, it's all the same uniform height, just halfway between the left and right ends of that, a plus b divided by 2 will be that value, should be the mean. And so that does make sense. Now, if we're going to find the variance by definition is sigma squared. That's what we use to represent it. And by definition, that's the expected value of x minus mu squared, which means we take x minus mu, square it, multiply by p of x, that's the PDF of x, and then integrate it from negative infinity to infinity. That's the definition. But there is another alternative formula that we're going to derive here. So first I'm going to use basically FOIL, or the distributive property, and square this out, expand it out. So you get x squared minus 2x mu plus mu squared. This is still the PDF of x. Distribute the PDF of x, and we got x squared times PDF of x minus 2x mu p of x plus mu squared p of x dx, and then break it into 3 integrals. Take the constants out front. We're going to leave the first one like it is, no constants there. This one has constants of negative 2 and mu, which I can bring out front. And we're left with integrating x times PDF of x dx. And over here we have the mu we can bring out front, and we're just integrating p of x. Now let's start with the right side here. If you integrate the PDF function from negative infinity to infinity, what do you get? Well, you get the area under that curve, which is exactly 1. So this integral here is 1, so get 1 minus x squared is x squared for the third term. Now here we're integrating x times p of x dx. You get the expected value of x, which is just mu. You take that mu times this mu, and we get mu squared has a coefficient -2. So we end up with -2 mu squared plus mu squared is -1 mu squared. And this first plus this first term here. Now this first term, we have the expected value of x squared. So what we get is the definition, it's the expected value of x minus mu squared. And another way to do it, it's the expected value of x squared minus the expected value of x quantity squared. In other words, the expected value of x squared minus mu squared. So let's use this alternative formula to find the variance of uniform distribution. Okay, and here are the details. So it's expected value of x squared minus mu squared. Now we already worked out what mu was just a minute ago. It's a plus b over 2, so I can just substitute that in. And this integral here is x squared times, well, p of x is 1 over b minus a. We can factor that out, and we're integrating x squared. Well, the antiderivative there is 1/3 x cubed, and we're going to evaluate from a to b. That's b cubed minus a cubed. That factors as a difference of 2 cubes is b minus a times a squared plus ab plus b squared. You might, if you don't remember that, you might just check this by multiplying this out using the distributive property, and you'll find that the middle terms all cancel, and you're only left with b cubed minus a cubed. Now, the b minus a is canceled here, so we have 1/3 times a squared plus ab plus b squared, and then we have this a plus b over 2 squared. So expand all this out and see what we get. Well, we get 1/3 times each of these. That's these first three terms. Here we're going to get minus 1/4 times a plus b squared. A plus b squared is a squared plus 2ab plus b squared, and multiplied by 1/4, you get these coefficients here, by -1/4 actually. Now combining, like, actually I factored out a 1/12, that leaves a 4 here, 4 here, 4 here, a 3 here, -3, -6, and -3 here. Combine like terms, and turns out you get a squared plus a -2ab plus b squared, which is b minus a, or a minus b, whichever, squared. Since b is bigger than a, I'll write it as b minus a squared. So it turns out that the mean is b plus a, or a plus b, divided by 2, and the length of the base is b minus a. It turns out that the variance is b minus a squared over 12. And of course that means that the standard deviation is the square root of that, so the standard deviation is just b minus a over square root of 12. Now how about the median? What does that mean? Well, the median of a distribution is an x value so that the probability to the left is 1/2. It's a different way of saying where the middle of that distribution is. So to find this, or to find any kind of inverse probability problem like this, we need to first find our CDF function. And our CDF function we know is 1 minus e to the minus lambda times the x value. So the x value I'm going to call mu tilde like this, which is one symbol for the median. So this is 1 minus e to the power negative lambda times the median. And that should be 1/2, because the probability that x is less than the median is exactly 1/2. That's the definition of the median. So we just need to solve this for the median, for mu tilde. Remember, lambda is going to be a given constant. So I subtract 1/2 from each side. That gives you 1 minus 1/2 is 1/2. Add e to the minus mu, or e to the minus lambda times the median, and that gives you this. Either think of this as rewrite as a logarithm, or take the logarithm of both sides. The log of e to the negative power cancels out, and you just get the power here, and you have a log of 1/2 here. Divide by negative lambda, and we have the answer here. I'm going to write this a slightly different way using some properties of exponents. Move the negative to the top, so we have -1 times the log of 1/2, which is log of 1/2 to the -1 power. 1/2 to the -1 power is 2, and so we just get the log of 2 divided by lambda, and so that's the median. And of course, if you integrated the function from 0, let's see, from, what is this? This is a uniform. This is an exponential, excuse me. If you integrate this exponential from 0 up to this median, you'll get 1/2 if you integrate it to PDF. All right, how can we find the mean of an exponential? Well, remember, mu is the mean. It's the expected value of x, or it's, in other words, x times the PDF of x, and then integrate over all x's. The only x's that matter are from 0 to infinity, and so we have x times the PDF. The PDF is lambda times e to the minus lambda x. Notice to do this, we're going to do this by parts. And so we let u be the x, dv, then becomes e to the minus lambda times lambda dx. We can stick a couple minuses in here to see this is minus e to the w dw, where w is minus lambda x. And so the antiderivative is minus e to the w, or in other words, minus e to the negative lambda x. du is just dx. So we have the integral of u dv, and so that gives us uv minus integral of v du. We're going to evaluate that from x equals 0 to x approaching infinity. And so, well, let's see, what does that give us? We get the u times the v, that's the x times the e minus the minus lambda x, that's the first term, minus the integral of the v times the du, which is just minus e to the minus lambda x. Minus out front is from the parts rule. And if we stick in another lambda here, another lambda with this minus that's already there, if I put a 1 over lambda out here, I again get e to the w dw, and so that is just e to the w. I got the minus 1 over lambda out front. We evaluate from 0 to as x approaches infinity for the whole thing. So for the minus, this part here, I'm plugging in 0. Okay. Actually, I don't know why that 1 over lambda should be here. But this term is 0, so it doesn't really matter. Let's see. No, that's okay. What am I doing? I want this. Yeah, this part should go here. X lambda da 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 da. Okay, it goes there and here. Okay. All right, so let's see, this 1 over lambda should be included. So I should take the function just like it is, take the limit as x goes to infinity. And then take this function here and let this go to 0. Okay, so let's check this out. Let's see what we got. This is e to the 0, which is 1, so this is minus lambda. This minus up here makes it, well, makes it plus lambda. Just write it this way. Plus 1 over lambda. Okay, and this one here, okay, we could write it like that. Okay, so here I could write this, I could factor out the e to the minus lambda and actually put it down in the denominator. So I'm going to actually use L'Hopital's rule, and the derivative in the top is, because this is the form infinity over infinity. The derivative of this 1 over lambda is 0. The derivative of x lambda is just lambda, so that part's right. and the lambdas cancel. Well, as the x goes to infinity, this denominator is still going to infinity. So this says the form lambda over infinity, which goes to 0, and so we end up with 1 over lambda. So the mean turns out to be 1 over lambda. Notice how this particular problem is fairly typical for these kinds of things that we're finding the mean of a distribution. First of all, it's very likely that we're talking about, well, at least to begin with, we're talking about an integral from -infinity to infinity. Sometimes we can effectively ignore part of that, but we're talking about an improper integral right off the bat. Secondly, it's very common in these kind of problems that you have to use integration by parts. So here's a real-world practical example of where we need a improper integral, and it's also a real-world example where integration by parts is useful. What about variance? How do we find that? So we're going to use L'Hopital's rule multiple times here, so I'm going to use the tabular method. Here I'm using the alternative formula that the sigma square is expected value of x squared minus mu squared. Now remember, we just found mu to be 1 over lambda. So the second part is 1 over lambda squared, and it was minus that. And the first part then is we're integrating x squared times the PDF. So that's x squared times lambda e to the minus lambda x. So that one right there we're going to need to use parts twice on. So I decided to use the tabular method. I put the x squared here. I put the lambda e to the minus lambda x for the dv part. Okay. And taking derivatives on the left side is real easy. Derivative of x squared is 2x. Another derivative is 2. Another derivative is 0. So that works out very, very nicely. Okay. I think it's going to be nicer if I just write this like this. Okay, and then over here on the antiderivative part, this is e to the w. Let's see, the lambda is just kind of out there. So when this is e to the w, if I put a minus lambda here, dx, then I need to put a minus, I need to multiply by minus 1 over lambda out front, and the e to the w part stays the same. So every time we take a derivative, an antiderivative on the right, we end up just multiplying by minus 1 over lambda. So this goes from lambda to minus 1, then to positive 1 over lambda, then to negative 1 over lambda squared for the coefficient. And remember, we're going to multiply across these diagonals, and we alternate plus minus plus is the way this tabular method works out. So this becomes x squared times minus e to the minus lambda x, that's the first term, minus 2x times 1 over lambda e to the minus lambda x, that's the second term. Then plus 2 times negative 1 over lambda squared e to the minus lambda x is the third term. And we don't evaluate that from x going from 0 to infinity, or as x approaches infinity. So let's see here. Okay, so I did a little cleaning up. I rewrote this as e to the minus lambda x in the bottom like that, and left the other polynomial part in the top. We still have this 1 over lambda squared, which is 1 over lambda quantity squared is 1 over lambda squared. And then we're evaluating this first part by taking a limit of this as lambda as x goes to infinity, and this second part here we're at 0. So let's look at the 0 part. The top, the first two terms go away to 0. The second one is just minus 2 over lambda squared, and the bottom one is e to the 0, which is 1. So this becomes 2 over lambda squared. That negative and that negative cancel, so we got plus 2 over lambda squared minus 1 over lambda squared, and this first limit is 0. To see that, we actually need to apply L'Hopital's rule twice, but we see after doing L'Hopital's rule twice, the numerator will be a constant. The bottom will also may have some coefficients, but it'll still have just e to the x, or lambda times x, so that denominator will go to 0, go to infinity. The numerator will be a constant once we've done L'Hopital's rule twice, and so that limit is 0. 2 over lambda squared minus 1 over lambda squared is 1 over lambda squared. So the variance, sigma squared, is 1 over lambda squared, which means the standard deviation, sigma, is just 1 over lambda. So this is kind of an interesting one. The mean is 1 over lambda, and the guess what? The standard deviation is also 1 over lambda. How about the skewness? Going to get some more practice doing integration by parts. So the skewness is, by definition, is the expected value of x minus mu over sigma cubed. So we take x minus mu over sigma cubed, multiply it by that f of x is the PDF. Okay, so that's lambda e to the minus lambda x dx. Mu is 1 over lambda. Sigma is that's a typo. Sigma is 1 over lambda as well. So multiply top and bottom by lambda, you just get lambda minus 1 cubed. And there's no fourth power here. I don't know if this is going to affect my answer or not. Let's see. So multiplying by 1 over lambda here cancels that out completely. This is lambda minus 1. I'm sorry. Lambda x minus 1 cubed, and then we have this part here. So I'm going to do parts 3 times using the tabular method, and I've got some that part's right. This part here is not quite right. So let's see. This should just be first power. Now every time we do an antiderivative here, once this is just like the one we did a while ago, every time we take an antiderivative we multiply by minus 1 over lambda. So this one has a coefficient of just minus 1. This one should have a coefficient of 1 over lambda. And they should be alternating a sign. This one, now it's a minus, and it's 1 over lambda square. And then this one down here is back to plus, and it's 1 over lambda cubed for the coefficient. Okay, I think we've got... Okay. Now, it's going to be better if I write these. Signs up here, so you can just look right down the diagonal. So go down the diagonal here. So the first term get this right, see what I'm doing here, is a little bit more. So it's that, and then this should be there's just negative 1 for this coefficient here. And the next one is 3 over lambda times 1 over lambda is just 3. So this should just be 3 here. Basically, I've got an extra lambda cube everywhere. If I get rid of that, I think I'm good to go. So we can get rid of that lambda cube. Should have lambda in it somewhere. Okay, so I think we have it all fixed now. Notice that we're taking derivatives here on the left side, and so here we get 3 times lambda x minus 1 to the second power times derivative inside, which is lambda. Take another derivative, 2 times the 3 lambda is 6 lambda. Then you got lambda x minus 1 to the first power times derivative inside makes that lambda, another lambda, so it makes it lambda squared. Take another derivative, the derivative that's just lambda, so let's get 6 lambda cubed, and another derivative gives you 0. So once we've done this down to 0, we can just multiply these here, here, and here, and add those up. We get 1, 2, 3, 4 terms. It's the way the tabular part works. And look, it's kind of interesting. Each time this lambda is going to be the right amount to cancel with the 1 over lambda to whatever power here. And so you can see what we get here by multiplying these products. Now, they all have a e to the minus lambda, which I can put in the denominator, and you evaluate it from 0 to infinity. You take the limit as this goes to infinity, this first part goes to 0. The e to the lambda x is going to dominate over that. Actually, you're going to use L'Hopital's rule 3 times, and we get that limit at 0. Over here, the part in parentheses is always negative 1. So we got negative 1 cubed is negative 1 times negative 1 is positive 1. I've still got my negative outside. Here I have negative 1 squared is positive 1 times negative 3 is negative 3. And negative 6 times negative 1 is positive 6, negative 6 in the end. 6 minus 6 cancels. Negative 3 plus 1 is negative 2. That negative makes it a positive 2. At 0 stays positive 2. And so we get the skewness is positive 2. So it's skewed to the right. And we looked at a graph of some sort of thing. It doesn't really matter. It turns out it doesn't matter what lambda is. And so this is an example of skew to the right. Long tail out to the right, kind of bunched up on the left, but then long tail to the right is a positively skewed distribution. So lots of practice there doing some parts. And I think in the next video I'll come back and do an example problem in a real world example.